Now let's talk a little bit about what this atmosphere of ours, of the planet we live on, can do or does for us to help or actually pose some impediments on what we want to learn about the universe, right? So remember the Earth, and then there is the blue sky, right? So there are certain layers of atmosphere. Okay, so some molecules of water, obviously I'm drawing them too big, and then we have a star somewhere, right, which is a point source, and it's spreading out the light, and at some point, it's supposed to come one of these rays of light, and it's going to meet molecules of water, and it's going to get scattered. The molecules of water, which behaves like prisms, like the one Newton first used to figure out that the white light or light coming from the sun is actually made out of the colors. So it's going to scatter that and basically blur the image, right? So yeah, so this is what we get from the ground, right? That is through Earth's atmosphere. All that motion of the molecules of, doesn't have to be just water, there is CO2 out there and many other kinds of molecules. They're going to scatter the light, and then the seeing of that star is going to be blurred, just like this one, right? So here's, for example, this exact field of view as seen from space, right, with Hubble Space Telescope. So this is from above the atmosphere, right? So there's nothing to blur that image. You see how sharp that image is, right? So there's turbulent airflow in Earth's atmosphere that distorts our view, causing the stars to appear to twinkle. Besides the fact that our eye it's not sensitive enough to see that there is not a point source anymore. It's a blob, okay? But for our eyes, it's still one dot. So there are very good reasons, right, for which we do want to go on top of mountains with our telescopes, because it's not going to be that windy. It's going to be less atmosphere to go through. Definitely far from the city lights or the stadium lights, right? It's going to be a dark side. And if we can find those mountains where there are very few cloudy nights, and Mauna Kea on Hawaii, Big Island, that's definitely one of those. So I don't know, that would be here somewhere in Hawaii. This is the chain of islands, and this is the big one, Hawaii, right? So yeah, that's the reason we need all these conditions, because otherwise every image that we're gonna need or want from the sky of the universe is going to be blurred, and we do want to gather as much information as possible with these images. So the cool thing is that we can actually get around, correct for the turbulence in the atmosphere. So we can correct for the seeing. Okay, so here's how that works. So if this is the Earth, and we have the layers of atmosphere, okay, and we have here, you know, a galaxy or maybe Neptune, okay, that is going to look blurred. However, if we're lucky and we have a star nearby, that means the light goes through the same kind of dance, right? Same kind of dance. And with computers, we can correct for that. So make a model of that scatter, and then apply that model to the extended source and correct. So we have apply that model and sharpen the image. This is what the adaptive optics does. So yeah, we kind of perfected that kind of method. That works really nicely, except for the situation when we're not lucky and we don't find the star that we need very close to that galaxy or the system of stars or something. And so in that situation, we're actually making our own bright star, which is basically a very powerful laser that is shooting through the sky, just like this one, right? So see, the other ones are tracks of stars. This is a long exposure image. So you basically see the stars moving in the sky. They don't move, but it's the Earth that is rotating around its axis, and so the whole celestial sphere seems to move, right? But we can actually create that star, and so, you know, all that laser will, you know, kind of do its own scatter dance, scattering by molecules in Earth's atmosphere. So again, model that and apply model, basically decompose that dance from the image, and you sharpen the image that we obtain with in this case the twin Keck telescopes. Okay, now a few words about, because you have heard about at least one telescope, we put them above the atmosphere, right? So one of them is Hubble Space Telescope, but it's not the only one. We went with telescopes that observe the universe in X-ray, and we had to put them above the atmosphere, that is in orbit around the Earth. We did Spitzer in infrared, and then in mid infrared. This one, Swift and Fermi, they go to higher energies, right? So this is wavelength is going there, so longer here, shorter wavelength, and also you go to the energy increases here. So we have here gamma ray, right? Okay. All right. Why do we need to put them in space? Well, the thing is, right? If you look at it, this is what the atmosphere does, and it does it. Actually, we're pretty lucky that it does it. It's the atmosphere does not allow, right? You see. Does not allow on the surface of the Earth pretty much anything, any type of light, but visible. Okay, look at that. Reaches the surface of the earth, and then the radio, the visible and the radio. All the other ones are stopped, right? Otherwise, we would be fried especially if the X-ray and gamma ray would reach the earth. So if we want to observe the universe and basically understand, is it anything out there that produces, very hot photons, very high energetic photons? Are there any really hot objects out there? We need to put an X-ray telescope in space, right? Infrared as well, right? Infrared reaches, so this would be, kind of near infrared, or the infrared type that has the shortest wavelength, right? It reaches the mountaintops. There is an airplane. This is an acronym for infrared observatory that works in an airplane, and we get to survey the universe in infrared. So, pretty cool stuff we thought about. But yeah, we actually need to make that effort and put, quite a lot of funds into launching this out there. Balloons and all that. We just try to make it as cheap as possible, but definitely they're needed. Now, why do we need to? This is one example. This is how, for example, our own galaxy, so this is Milky Way, and how this Milky Way looks like in different wavelengths. Here's what we have here. This is in radio. This is in X-ray. This is in gamma ray. And this is in infrared. This is what these things stand for. And this is our own Milky Way, our own galaxy. This is the disk. And then we have a halo with lots of things happening, both in the disk, and the halo, and they're different in different wavelengths. For example, this is accretion of material onto a black hole, right? And you wouldn't be able to actually find this, right? It's missing. Look at that. We're gonna be missing black holes in radio. Sorry, also in invisible as well. In X-ray, you wouldn't be able to see all these hot, or maybe not as hot, but it's dust, cosmic dust. See how much of it is in the halo, right? We didn't even know that that thing is there. Okay, yeah. So we're gonna find out about these things actually in future chapters. Just I wanted to give you a sense of how different our own Milky Way looks in the different eyes that we now have the opportunity to use when we want to study our own galaxy. Here's something very interesting about how we actually gather all these different types of photons, or the light that is not invisible. And here's an example of how the X-ray telescopes work. So the X-rays, they're very energetic. So, right, you have an X-ray photon is going to fry whatever it meets. And so we're not gonna kind of put the bucket here, right, to catch it. So basically it's hard to catch. And so in this situation, we use these nested mirrors, okay, which are going to deflect the X-ray. So we work at the so-called grazing incidence, and we just kind of slow them down first, right? They slow down. So first down the X-ray photons, and later on we kind of catch them, we put them into focus, and this would be the detector, right? Otherwise it just goes through, right? So if you just have the detector kind of perpendicular to the direction in which the X-ray is coming, we're not going to be able to count it, we're not going to be able to measure it. And so first we deflect them little by little. So that's a very interesting technique. We were only able to come up with this maybe like 20 years ago. So it's very, very recent, right? So special mirrors, you can't just make a dish and say, okay, let's catch those X-rays or gamma rays for that matter. All right. Here's another example of, for example, why we need the ultraviolet observations. And here are the space telescopes that we use. They're not working anymore. Galax has been decommissioned. HST, Hubble Space Telescope, is still there. So that's where much of the recent work in ultraviolet was obtained. What do we use or need the ultraviolet radiation for? This is how we detect the really high energy dust or gas features, and this is where basically the stellar nurseries happen. So here's an example. This is a star chart of Orion, and look at that. This is the Orion belt. I showed you previously that part of that chart. So that's just a location of some stars, right? So that's a constellation if you want. This is how we see in the visible. Okay, so you don't see that much actually, just star, just a bunch of stars. But I showed you that just under the Orion belt, here is the Orion Nebula. Which is gas, where we figured out later by actually observing in infrared and ultraviolet where stars are born. And we were able to detect that nursery, that dust that usually appears when stars are formed, with infrared observations and with ultraviolet observations. So nothing here, right? You see? Nothing invisible. But quite a lot of things, right? So clearly there, clouds of gas with some properties that we were able to measure that told us the stars, new stars are born. And here's, for example, a radio dish, actually the largest stirrable thing on the surface of the Earth, and that is in West Virginia. That's the Greenback Telescope. That's about 3 hours away from Harrisonburg. So hey, drive out there, look it up, drive out there if you get a chance. There's a really beautiful site there, and of course that's me. And I was here on this platform, sorry, yes, of course, on this planet. And yeah, I did some observations with the Greenback telescope. So that's radio. All right, so millimeter, centimeter, wavelengths, right? Or if you want to think of these things in terms of frequency, we get gigahertz, right? So 10 to the 9 hertz. That's the frequency of observations. Why do they need to be so big? I told you this Green Bank telescope, this is the largest stirrable, that is movable thing that exists on the surface of the Earth, and that is in West Virginia. Why so big? Why so big? Here are some examples, some of calculations. Why do we need to have this, especially in the radio? So here's what we have. Here are the calculations of the angular resolution. Remember that formula? But now we're going to do it for JCMT. It's one of the radio telescopes on Mauna Kea site. And that's how big that telescope is, 15 meters, right? And that's the wavelength of the radio light. Okay, so if you use that kind of wavelength and for that size of telescope, you plug them into the formula, you're gonna get an angular separation resolution. You can't see anything that is separated by less than basically 17 arc seconds. Now, you do the same with the Hubble Space Telescope, which is much smaller. Than the radio dish. But look at the wavelength, right? This is the optical or visible. Okay, it's a much smaller, right? Shorter wavelength, right? So this is shorter wavelength. So you plug them back into this formula, and you find that you can actually distinguish things with the Hubble Space Telescope. You can distinguish things that are less than just a few hundreds of an arc second away from one another, right? So, because wavelengths, radio wavelengths are large, then you need, right, very large telescopes for small values of theta, right? Because this is what we want, right? This is the definition of good resolution or sharp images. So this is huge, right? Almost a kilometer, if not more, I forgot, right? This is in Arecibo in Puerto Rico. That's basically a valley that is wired, and this is how that radio telescope was put together. So yeah, that is the largest radio telescope, but it's immovable, right? Compare that with the largest stirrable, movable thing, which was at Green Banks. Just, some examples. So because so with especially for radio observations, we can actually allow 2 or more telescopes to work together, right? So we're going to simulate with that a very long baseline. So while we can't make this big of a dish, so not a large dish, but large baseline, right? So we have baseline. So basically we simulate a large diameter of a telescope, and it's working pretty nice, right? So if this is a very large, then it's going to be a small resolution at the end. Fine. Would be nice to kind of fill up this area with telescope, right? So add more radio dishes here, and you increase, the gathering area, the collecting area of light, and that's going to offer even more information about the objects we observe in radio. But anyway, those are impressive sights, very impressive sights. I've been on one of those dishes as well. It's an amazing life to be an astronomer. How about the future? Very soon, those super telescopes are going to come, and this is one that is it's expected to be commissioned in 2029, so just kind of around the corner. This is called the Giant Magellan Telescope. Okay, so what do we have here? 6 dishes. So basically, one we have on the Earth. That's this is 5 meter or so, or more, or 8. I forgot. But overall, we get, this thing is going to work as one telescope of a diameter of about 25 meter, which is amazing, or about 80 foot if you're more familiar with those kind of units, which is amazing, right? So that is going to be able to produce images that are 10 times sharper than the Hubble Space Telescope will produce for us. So yeah, in case you're wondering what the future of the astronomy will look in the next century, and not even just kind of starting with the 21st century, this is going to be one of the windows. Speaking about plans, we are thinking about and some other telescopes as well, and we call that the age of extremely large telescope. And I'm gonna have you try to guess what these names mean, but I'm not gonna let you guess for longer. So remember, this one is the Giant Magellan Telescope. This is GMT. What do you think TMT is going to be? It's the 30 meter telescope. Now take a guess at this one. I'll tell you what it is. Extremely large telescope. So you, the future billionaires of this world, you're going to fund all these crazy, wonderful ideas, and your names are going to be on these wonderful telescopes as well. And after we build this, we're going to go to the moon and basically increase the baseline, remember? So basically increase the diameter, and if we do that, we're going to have a very small separation, or that's going to be best resolution ever. So these are our dreams, and hey, why not you being one of those who are going to help these dreams become reality.